So any doubt regarding the prerequisite? Now today what we will do, we will discuss some basic of slope deflection, and we will start with our first chapter, that is slope deflection determination using moment area method. Okay. Now suppose we will consider this is the simply supported beam. This is the simply supported beam. And if I apply some loading on that simply supported beam, suppose if UDL is acting, okay, UDL is acting on this simply supported beam. UDL is there on this simply supported beam. So what will happen? Yes, simply supported beam is there, and if that simply supported beam, it is subjected to the UDL, what will happen due to that loading? Yes, Rajkumar.
Stresses are produced, sir.
Okay, first, very good. Stresses are produced. Stresses are produced. Okay. Means that will be bending stresses are produced. Okay, bending stresses will be produced. Then again, second parameter, first, definitely bending stresses will be induced in that particular beam. Correct. Again, what will happen? What will happen? So before inducing the stresses, what will happen? Before developing the stresses, what will happen? This is the load. Suppose this is 10 kilonewton per meter, and this is the span of suppose 4 meter. Okay. So at the lateral stages, stresses will be induced. But before that, immediately after the application of load, what will happen? Yes. Akrati, Akash. Zoe.
Yes, sir.
Due to the UDL on a simply supported beam, what will happen? Initially काय होईल जर लोड अप्लाय केला आपण सिम्पली सपोर्टेड बीम वरती तर so due to the loading condition, initially it will bend now. So due to the loading condition, initially the simply supported beam, it will have the bending. It will bend initially. Okay, due to the external loading condition. Now, if you see this particular bending, so initial position of beam, it is, we can say AB. This is the initial position, and due to the application of external load, it will have the bending. Now this is the bending. Okay, suppose initial position is, this is, we can say XX initial position. Due to the external loading condition, it will have the bending. Now this vertical distance or the vertical displacement is seen, vertical distance between initial position to the bending position. So this vertical intercept, it is nothing but our deflection. It is nothing but the deflection, and that we have to find out. And that deflection, this deflection, it should be the within permissible limit. So as the structure is there, it may be 1D structure, 2D structure, or 3D structure. So we can't avoid the deflection. So definitely deflection will be there. Okay, deflection will be there. So that deflection value or that displacement value, it should be within the permissible limit. It should be within the permissible limit. So what are that permissible limit, that we will also see. Now, due to the bending of that particular beam, the curve is formed, and that curve, it is called as the elastic curve. Okay, so due to the external load, beam will bend, and that curve, it is called as the elastic curve. Okay, and if you find out the vertical distance at each and every point on that elastic curve with respect to the original position, you will get the deflection at that particular point. Suppose this will be y1, this will be y2. So these are the respective deflection at that various points, and the curve, it is the elastic curve. Okay, next it is the slope. Now once you draw the elastic curve, and if you measure the angle, with respect to the original position of the beam. Now this is the original position of the beam AB, and this is the elastic curve. So if you measure this angle theta A, so this is nothing but the slope at end A. Okay, this theta A, it is nothing but the slope at end A. Similarly, theta B, it is the slope present at a point B. So how to find out the slope? Okay, so first draw the elastic curve due to the loading condition, then draw the tangent. So next what we have to do, we have to draw the tangent. Now this is the tangent. So where we have to draw the tangent? At a point where we want the slope. Suppose we have to find out slope at A, then draw the tangent from point A on that elastic curve. Okay, this is the elastic curve. So the angle made with respect to that elastic curve with respect to the normal position, so that angle is nothing but the slope. And generally that slope, it is given in the unit, and that unit is radian. Okay, that unit is radian. Means after the calculation, the answer you will get for the slope, and that unit should be in the radians. Okay, if your load, it is in kilonewton, length of beam, it is in meter, then your slope theta, it should be in radians. It should be in the radians. Okay, if in some MCQs or in some numerical, if they have given the value of slope, that angle theta, it is equal to say 18 degree. So how to convert this degree into the radian? How to convert degree into radian?
Multiplied by pi by 180.
Very good. Multiply with pi divided by 180. Correct. Multiply with pi divided by 180 if the slope is there in degree. Okay, so this is for the slope. The next point we have to remember is that at a point of maximum deflection, your slope will be 0. Okay, at a point of maximum deflection, your slope should be 0. Now suppose this is the simply supported beam subjected to the central point. Okay, now loading is symmetrical, somewhat loading is symmetrical. Now at center, at this particular center, deflection is what? Maximum. So maximum deflection is seen at the center. Now at this particular point, and this is the elastic curve, of a given beam. Now if I draw the tangent at that particular point C on an elastic curve, so that tangent will be what? Horizontal line. Tangent will be the horizontal line. Horizontal line means what? Our theta angle will be what? 0. Theta will be 0. So that's why one point we have to remember is that at a point of maximum deflection, the slope must be 0. Okay, slope must be 0 means at a point of maximum deflection at y max, dy by dx is equal to 0. Dy by dx is equal to 0, and dy by dx is nothing but the slope. So as tangent is the horizontal line, theta is equal to 0 degree, so slope must be 0. Okay, so this is the what is the deflection, what is the slope, and at a point of maximum deflection, slope must be 0. Now we will discuss the permissible limit. So what are the permissible limit for the given deflection in case of beam? Okay, so deflection we have seen. So this is the vertical distance between the axis of beam before bending and after bending. Okay, this is the axis before bending, and this is the axis after bending. So this vertical distance here, it is YC. It is nothing but the deflection, or we can say vertical displacement. Now as per the BIS, Bureau of Indian Standard, so what is the permissible value of deflection we are having? So there are two clauses, but the permissible deflection, it should be less than or equal to L by 350 or 20 mm, whichever is less, where L it is the span of the beam. Okay, suppose the span is there 3 meter, so that you have to convert that meter into mm by multiplying with 1000. Okay, so L by 350 or 20 mm, whichever is less, that is the permissible limit. Now if you see the clause, if you refer the IS 456, IS 456 2000. So this is the IS code given by the BIS. In that IS code, you have to study this IS code in SD2, design of RCC. Okay. So in that IS code, they have given the two clauses or two statement. Now we will read that statement. First statement. So what is the first statement? Final deflection due to the all loads, including effect of temperature, then creep, sinkage, measured from the as-cast level of the supports of floors, roofs, and all other horizontal members should not normally exceed. Okay, should not normally exceed means it should be less than or equal to. Okay, so for total final deflection due to the all the combination of load, so that deflection it should be less than or equal to L by 250. Okay, L by 250, where L it is the span of that particular member and it should be in mm. Okay, so this is the first point. So this is the deflection due to the final deflection due to the all the combination of loads. It may be your dead load is there, live load is there. So due to the temperature effect, if it is the steel structure, so definitely due to the temperature variation, there will be contraction and expansion. So all that load, combination of all that load, the final deflection restricted to L by 250. And the second clause is that deflection including effect of temperature, creep, shrinkage occurring after the erection of partitions and application of finishes should not be exceed L by 350 or 20 mm, whichever is less. Now, first it is final deflection due to the all the loads, and the second clause it is due to the various effects. Effects as it may be temperature variation, it may be creep, okay, it may be shrinkage, it may be the stresses or deflection induced due to the erection of steel structural members or due to the application of finishes. Means if you apply the, we can say plastering or pointing, so that finishes, or if you have performed the flooring, so that finishes. So your deflection should restrict it to L by 350 or 20 mm, whichever is less. Okay. So L by 350, suppose in one case the span is 3 meter, or we can say 3.5 meter. Okay, 3.5 meter is the span. So 3.5 meter you have to convert into the mm. So 3.5 into 10 to the power 3. So it will be what? 3500 divided by 350, isn't it? So that will be what? It will be 10 mm. Okay. So as per the L by 350, the answer is 10 mm. And what is the clause is there? L by 350 or 20 mm, whichever is less. Now here, after the calculation, deflection is 10 mm and here it is 20 mm. So out of that 10 and 20, whichever is less, that we have to choose. Means here 10 mm it is the permissible deflection. 10 mm it is the permissible deflection. So these clauses you have to study in detail at your SD2 subject. Okay. So right now you remember L by 350 or 20 mm, whichever is less, and final deflection it is L by 250. It is more than sufficient. You may expect one of the MCQ based on the permissible values. Okay. Now we will start with the moment area method. Now this moment area method, it is used to determine the slope and deflection at a particular point, in determinate structure and indeterminate structure. Okay. Now in case of Macauley's method, now tell me in Macauley's method कोणकोणत्या बीम साठी तुम्ही अप्लाय केली होती सांगा. So for which kind of beam you have applied the Macauley's method? Yes. Adinath, Macauley's method, it is applicable to option A, simply supported beam, option 2, cantilever beam, option 3, overhanging beam, option 4, all of the above. Option 4 is all of the above. Sanga. Yes, Akash. Yes, Adinath.
All of the above, sir.
All of the above. Yes, Macauley's method or double integration method, it is applicable to the determinate structure only. Okay, so we can say that was the one of the limitation of Macauley's method. So Macauley's method, it is restricted to the determinate structure. That may be our simply supported beam, cantilever beam, or hanging beam. So that drawback or that limitation is overcome in moment area method. Now in this moment area method, you can apply this moment area method to find out the slope and deflection at a particular point in case of determinate structure as well as indeterminate structure. Means you can find out the slope deflection of simply supported beam, cantilever beam, overhanging beam, as well as propped cantilever, then fixed beam, as well as the continuous beam. Okay. Now this moment area method, it consists of two theorems. Okay. This particular method, it depends on two theorems, and that theorems are proposed by the Morse. That theorems are proposed by the Morse. So that's why it is called as the Morse theorem. Okay. So this method, it is based on the two theorems, two statements, and that theorems are proposed by the Morse. So that's why theorems are called as the Morse theorem. Theorems are called as the Morse theorem. Now we'll discuss the first theorem one by one. We'll discuss now moment area theorem number one, or we can say Morse theorem number one. Now first theorem, first point we have to remember that first theorem give us the slope. First theorem, it will give us the slope dy by dx. Slope is nothing but the theta, or we can say it is nothing but derivative of deflection dy by dx. Dy by dx. Okay. Now we will see the statement, then we will discuss in detail. So what is the statement? Moment area theorem states that change in slope between any 2 points on an elastic curve is equal to the area of m by ei diagram between 2 points. Okay. So this is the statement of first moment area theorem. So what is the statement? Change in slope. In short, what was the statement? Change in slope is equal to area under m by ei diagram. Okay. If you have to find out the slope, what we have to find out? We have to find out the area of m by ei diagram. Okay. Area of m by ei diagram. Now can anyone tell me what is m by ei diagram? Frankile, what is m divided by ei diagram? ऐकलंय कुठं? m divided by ei diagram. Okay, I will give 4 options. M by ei diagram is option 1 BMD. Okay, option 1 BMD, option 2 SFD, option 3 BMD divided by ei, and option 4 is none of the above. None of the above. सांगा.
BMD, sir.
ऑप्शन 1 म्हणतो ना तू?
Yes, sir.
Okay.
Option C, sir.
Option C, correct, Vaibhav. Now this m is nothing but it is our bending moment. Okay, m is nothing but the bending moment. So m divided by ei is nothing but our BMD divided by ei. So it just, what is m by ei diagram, we will discuss in the next slide in detail. So in short, this m by ei diagram is nothing but your bending moment diagram, or bending moment at each and every point. We have to find out the bending moment. Okay, suppose simply supported beam subjected to UDL. This is our BMD, and this particular value is at center, it is WL square by 8. Okay, WL square by 8. Now this is bending moment. So if I have to draw the m by ei diagram for this particular beam, then what I have to do is bending moment divided by ei. So bending moment, it is as it is WL square by 8 divided by ei. So it will be what? WL square divided by 8 ei. This is m divided by ei, or you can remember BMD divided by ei. BMD divided by ei. Okay. So theorem number 1, it gives us the slope, that is theta or dy by dx. And what is the statement in short? So change in slope between 2 points is equal to area under m by EI diagram between that 2 points. Suppose there are 2 points, theta 1 and theta 2. If you have to find out the slope, change in slope between these 2 points, then what we have to find out? We have to find out the area under m by EI diagram between point 1 to 2. So only these 2 points we have to consider to find out the area. So as we have to find out the change in slope between the 2 points. So here what is important? Point of consideration. Point of consideration is very much important. जर तुम्ही 2 पॉइंट घेताय, त्याचा जर तुम्हाला स्लोप पाहिजे असेल तर त्या 2 पॉइंट मधलाच तुम्हाला एरिया फाइंड आउट करायचा आहे. एरिया कुठून फाइंड आउट करणार? m by EI diagram madla area. Okay. Now we'll see in detail. Now suppose here simply supported beam is there, subjected to UDL on entire span. And if I have to find out, the change in slope between 2 points, suppose B and A. Okay. So what is the statement? Change in slope, it is equal to area between m by EI diagram of 2 points. Now our point of consideration will be what? Point A and point B. So what is change in slope? Slope of second point minus slope of first point. So theta B minus theta A. So change in slope is equal to area of BMD between A and B divided by EI. Now this is BMD parabolic curve. Okay, this is the BMD parabolic curve. Now this is point A, this is point B. Now we have to find out the area. But which area we have to find out? Between point A to point B, means this total diagram, parabolic curve. Okay, parabolic curve, this for total diagram of parabolic curve, we have to find out the area divided by EI, So this is the first theorem. In short, what you have to remember, for the slope, find out the area of BMD divided by EI. Okay. Area of m by EI diagram म्हणा किंवा area of BMD divided by EI म्हणा, one and the same. For slope, we want the area of m by EI diagram. So exam मध्ये विचारलेला आहे. So in case of moment area method, at a particular point to get the slope, we need to find out option A, bending moment at a point, option B, area at that particular point, option C, area of m by EI diagram between the 2 points of consideration. Okay, so that we needed. Point महत्वाचे आहेत, point A, point B. So in BMD, find out the area between these 2 points, B and this is A. So area between these 2 points, it is very much important to find out the slope. Okay, this is the first statement or the first theorem. Second theorem, it will give us the deflection, or we can say Y. So for deflection, so we can say in short, I will tell you. So for deflection, we have to find out moment of the area. Okay, we have to find out the moment of area. In for slope, we have to find out area of m by EI diagram. For deflection, we have to find out moment of the area. Okay, so this is the statement they have given. If A and B are the 2 points on the deflected shape of the beam, then vertical distance of B from tangent drawn to the elastic curve at point A means it is nothing but the deflection of B. Is equal to moment of area of BMD between A and B about the vertical line from point B divided by EI. Means what? Now here we know that to find out the deflection, we have to consider the moment of the area. एवढं आपल्याला समजलंय. स्लोप साठी एरिया फाइंड आउट करायचंय आणि डिफ्लेक्शन साठी मोमेंट फाइंड आउट करायचंय. नाउ we have to take the moment. We have to take the moment of the area. So definitely there will be 2 points. Suppose this is point A, this is point B, and if I want to find out deflection of this B point, then I have to consider the moment of this particular area between point A and B, but consider the moment about the point where we want the deflection. ज्या पॉइंटला तुम्हाला डिफ्लेक्शन फाइंड आउट करायचं आहे. So take the moment at that particular point only. Means consider the moment about the point where we want the deflection. Okay. So again, we will consider the same example. Simply supported beam subjected to UDL. Now here, if we want the deflection at a point B, if we want the deflection at a point B, so what we have to consider? Again, we need 2 points of consideration. So first point is A, second point is B. Now area will be what? Area of point A to the area of point B. So moment of this particular area, we have to consider about point B. We have to consider about point B. समजते का बघा, एरिया कोणता कन्सिडर करायचा आहे? A to B मधला पॅराबोलिक, टोटल पॅराबोलिक कर्व. So that is the area. But for deflection, what we want? We have to consider moment of this area. Okay, means perpendicular distance of this particular diagram from point B. Point B का घेतला? Because we want the deflection at a point B. So that's why we have to consider the moment about point B where we want the deflection. समजून घ्या व्यवस्थित. आपण पॉइंट ए ला मुवमेंट फाइंड आउट करत नाही, कुठं फाइंड आउट करतोय? पॉइंट बी ला. व्हाय? बिकॉज वी वॉन्ट द डिफ्लेक्शन ऍट अ पॉइंट बी. We want the deflection at a point B. So always consider movement of area at a point where we want the deflection. Okay, where we want the deflection. Now, based on the standard loading condition, it may be your moment, point load, UDL. So there are various diagrams you will see in the BMD. So what will be the centroidal distances, how to calculate the area, that we will discuss. Now, can anyone tell me, if this is the parabolic curve, so what is the area of parabolic curve? What is the area of parabola? This particular diagram, parabolic curve. Anyone? Area of parabolic curve. Because if in a numerical or in MCQ, if there is a UDL, then definitely you will get the parabolic curve like this. This is the second degree curve. So you should know how to find out the area. So that diagram we will discuss now. Okay. Now this moment area method, it is suitable for cantilever beam, simply supported beam, okay, having symmetrical loading conditions, as well as fixed beam, means statically indeterminate beams also. So what is the advantage of this moment area method? We can apply this method for statically determinate structure as well as statically indeterminate structure as well. Okay. For both the structure, you can apply this method. And this particular method, it's suitable for a beam for which area and CG of that area of BMD can be found easily. Means what? If the nature of BMD is triangle, rectangle, parabolic curve, or we can say hyperbolic curve. So figure should be the regular figure or the diagram of BMD. If these are the regular figure, then you can find out its area, then you can find out its centroidal distance. Then it will be easy to calculate using this moment area method. Okay. In short, this particular method, moment area method, it is not suitable for triangular loading and irregular loading conditions. So for irregular loading conditions, your BMD will be, suppose BMD is somewhat like this. So for this irregular diagram, you don't know how to find out the area and we don't know how to find out the centroidal distance. So you can find out using the first principle by taking the strip, by performing the integration, but that is the time consuming process. So this method, it is applicable only for the symmetrical loading conditions. For BMD, for which we know the area as well as centroidal distances. Okay. Now we will discuss the M by ER diagram. Now this is the cantilever beam subjected to the point load at free end. Now we will see what is the difference between M diagram and M by ER diagram. Now what is the nature of BMD or M diagram for this particular cantilever? BMD कशी असेल?
सर बी ला 0 असेल.
बी ला 0 असेल. व्हेरी गुड. ओके, बी ला 0 असेल. Very nice. Again, what about A? I will give three options here. Hmm. Out of option 1, 2, 3, 4, which one is correct?
Second one, sir.
Second one or two,
Second.
correct? Yes, yes, correct. Second one means what? It is the triangle. It is the triangle. Now we know that the bending moment will be maximum at fixed support. Fixed support la bending moment maximum असेल and T काय असणार P into L. So PL it is nothing but the maximum bending moment at fixed support, or we can say bending moment at fixed support. Now this is nothing but the Yum diagram. This is nothing but the Yum diagram, or we can say this is, in simple word, this is BMD. Yum diagram is nothing but the BMD. Moment mana किंवा bending moment mana. Yum diagram or BMD. Now what is Yum by EI diagram? The nature will be the same in this case, as we will consider EI is constant. Suppose EI is constant. EI is constant. If I is variable, suppose for some portion it is twice of I, and for remaining portion it is suppose 3I. What it indicates? It will indicates the change in cross section. Okay, so variation of moment of inertia indicates change in cross section. Okay, suppose for first left half span the moment of inertia is twice of I, and for the second half span if the moment of inertia is 3 times of I. So what it indicates? It will indicates change in cross section. That I will explain. Suppose this is the rectangular cross section. Okay, this is the rectangular cross section. Then we know that moment of inertia is what? BD cube by 12. Moment of inertia of rectangular portion is what? BD cube by 12. Now what is B into D? This is the cross sectional area. Okay, means if there is a change in moment of inertia, it will reflect, or it will gives us the change in cross section. If EI is constant, the nature of BMD and nature of Yum by EI diagram, it will be same. इथं ही triangle आहे, इथं ही triangle आहे. Change काय होणार मग? So this bending moment will be PL divided by EI. So what we have to perform? Bending moment divided by EI only. That you have to perform, as EI is constant. As EI is constant. Suppose for some portion cross section is different, and for some portion cross section is different. In that case, the nature of your Yum by EI diagram, it will varies. That we'll discuss in the next slide. Okay, so if EI is constant, काय लक्षात ठेवायचं बघा, if EI is constant, then both diagram, Yum diagram means your BMD and Yum by EI diagram, it will have the same nature. Okay, it will have the same nature, or it will have the same figure. Okay, so the value of bending moment will be PL by EI. This will be triangle, this will be triangle. Now, so if I consider again cantilever beam subjected to point load at free end. Now here for first 3 meter cross section is 3I, and for second 3 meter cross section is twice of I. Now BMD, it will be a triangle. BMD, it will be a triangle. Okay, and bending moment at this particular fixed support, it will be what? This 50 into 6, isn't it? 50 into 6. So that will be 300 kilonewton meter. Now your Yum by EI diagram, it will change. Why it will change? Because here EI is not constant. Flexural rigidity constant nahi hai. इथं काय आहे? 3 EI. Okay, and for the next half span it is twice of EI. Means there is a change in cross section. So nature of Yum by EI diagram, it will vary. It will vary at a junction. Okay, nature of Yum by EI diagram, it will vary at a junction where there is a change in cross section. इथं बघा, there is a change in cross section. Towards left it is 3I, towards right it is twice of I. At this particular junction there will be two bending moment. समजते का बघा, at this particular junction there are two cross sections, there will be two bending moment. Now what we will do? First we will find out the bending moment due to twice of I. So how to find out the bending moment? Bending moment will be the same at this particular point. काय असेल? At this particular section, what is the bending moment? सांगा first. Bending moment काय असेल त्या portion ची?
9.
बेंडिंग मोमेंट फोर्स इंटू परपेंडिकुलर डिस्टन्स हा राइट पोर्शन कन्सिडर करा आणि सांगा. यस, फोर्स इंटू परपेंडिकुलर डिस्टन्स. Yes, Rajkumar.
150 kilonewton.
150.
Yes, correct. 150. 50 into 3, 150, बरोबर. So 150 kilonewton meter. Now this is nothing but the m, or we can say bending moment. What we want? We want bending moment divided by EI. Now see, at this particular junction there are 2 EI. So we'll find out first m by EI due to cross section of twice of y. So this 150 divided by twice of EI. मग ते काय झालं? 150 by 2, 75 divided by EI. So this is due to the twice of I cross section. Similarly, again, bending moment will be the same. 150 divided by, now cross section is what? 3I. 3 EI. Okay. So that will be what? 150 by 3, 50 divided by EI. Clear? So this is the m by EI diagram. Okay, m by EI diagram. Bending moment will be constant throughout the point or throughout that junction. Force into perpendicular distance. So what we want here? We want bending moment divided by EI. So first, due to the twice of EI, so that will be 75 EI. Second, due to the 3 times EI, so that will be 50 by EI. Now tell me why this is 100 by EI. Bending moment at fixed support. हे 100 by EI कसं आलं सांगा. कोण एक्सप्लेन करेल? Yes, why this is 100 by EI at fixed support?
Fifteen into 6
Yes,
divided by 3.
very good. 50 into 6. Now force into perpendicular distance. That is, force is 50, perpendicular distance is 6. Correct. And what is the cross section at fixed support? That will be 3, isn't it? That will be 3. So that's why 3 EI. मग किती येतं ते? 300 by 3, 100 by EI. 100 by EI. Okay, and this is the m by EI diagram. If there is a change in cross section, now this is the variation. This is a BMD, and this is BMD divided by EI. Means nature of BMD will